Worked on an object given a force versus displacement graph.
Okay. No, that's so wrong. You're gonna stick the whole thing in it.
We already did that. It's just finding the area of this graph. But let's do one that's tougher, okay? Let's say that this is
I'm
our...
going.
God, let me show you. Go like this. That's so stupid. Why would you do that? Okay, you say something. I want to see it fail.
Let's say our graph looks more like
It's 6
this.
centimeters from here. So from there.
So we want to find the work done on the object given this variable force acting over this distance. So what property of the graph gives us that work?
Alright, right there.
The slope of the tangent?
Not the slope of the tangent. What property of the graph gave us
Oh, the
the
area.
work? Yeah, the area. Because it's the force times that distance, okay? This isn't a regular shape, so we can't just simply pull out our triangle equation or our area of a square, rectangle, or whatever equation. We have to do something a bit more complicated. It doesn't change the fact, though, that it's the area of the graph. It's the area of the force versus distance graph. So we gotta find this area.
I swear to God, if the velocity is 5.4, I could have.
Well, this is a regular shape, but it's not going to be able to cut it into trapezoids. So what do you think? What can we do here?
Calculator again. I've done this like 5 times. I'm sorry, Todd. I'm very stressed.
How would you find, let's say that I gave you a jug, right? Let's say I gave you a cylinder, a perfect cylinder. Okay? And I asked you to find the volume of it. Well, you just pull out your formula for the volume of a cylinder and you calculate, right? But what if I gave you some kind of a weird, irregular shape? Say I wanted you to find the volume of this. Is there a single equation called the volume of a kettle that you could use? No, so what would you have to do?
Yo, you're 7 meters per second.
Yeah, you have to break it down. You'd have to estimate it, right? So the smaller the pieces you break it down into, the more precise your calculation is going to be, right? If I broke this down into 1 millimeter cubes, then it would be a pretty precise calculation. Or if I could somehow fill this completely with water, then take all the water that I put in here, dump it out, and put it into something else, like a graduated cylinder, I'd be able to see exactly what the volume is, right? So the idea is that we can slice this up into little tiny pieces, cut up into little tiny pieces, and if we can tell the volume of each piece, it's just a matter of summing all those pieces up. Same with this area. So we're going to cut this area up into little tiny pieces. So we could just, imagine this is on graph paper, so we can slice it up. So slice it up into these slices. Slice it this way too if you want. Oops. Okay, and then just choose one of these little boxes. So I'll draw a few boxes on here. This is really just composed of a whole bunch of little boxes. Now when you get to the end, you've got partial boxes. You'll have to just estimate those, right? That's about, I don't know, half a box. That's about half a box. This one is just maybe a third of a box, and so on. So each of these little boxes,
Number 3.
each of these little boxes is worth a certain amount of energy. How can we figure out the amount of energy that each little box is worth?
You calculate the area of one box.
The area of the box, right. So on the bottom, it's a distance, and up here, it's a force. Now I don't have numbers on here, but each little box might be, 1 centimeter wide and 0.1 newtons high or something like that. At any rate, you can calculate the amount of work on each box has. And then your total work done is just the sum of all the boxes. Now, if a box is above our d-axis here, it gives you positive work. What about below the d-axis?
Negative work.
Negative work, that's right. It's a negative area. So just like when we did it before, you know, any areas, negative areas of the velocity time graph gave you a negative displacement. Same idea here. Any negative areas down here gives you negative work. So that's one method of doing it. Now next year in calculus, you'll learn integration. Integration is a method that you can use if you know this function. If you know the function, then you can figure out exactly what the area is using a method called integration, which you learn in calculus first year university. And basically, integration is slicing this up into slices and adding all the slices up. But integration allows you to make the slices infinitely thin. So that gives you infinite precision, extreme precision, because imagine just an infinitely thin number of slices all added up. Then you can eat that, not saying easily, but you can then calculate the area of that. Okay, so that's how you would do a complicated shape. You've got to estimate, which means that you'll all have different answers, but they'll all be in the same ballpark, like as if you were all doing tangent lines, same idea. There's only one specific answer, but it's estimated, so it's going to be a range.